Welcome. This is Dr. Martin, and I'm going to talk about Chapter 14 today. And this chapter is about flip-flop state assignment. And there are some learning objectives that I would like you to learn, so let's jump into it. Okay. So the learning objectives are, number one, I want you to be able to state how flip-flop state assignment impacts the target hardware. And the answer to that's pretty straightforward. It can certainly change the size of the required hardware. And so that's one reason why we want to give some thought to flip-flop state assignment, because it can simplify our hardware. And in some situations, that's a very desirable thing to do. Secondly, you need to be able to demonstrate how to make adjacent state assignments using a K-map. And adjacent assignments are simply defined by flip-flop encoding that only differs by 1 bit change. So for instance, if the first state S0 is 000, then the next state could be, say, if it's 3 flip-flops, then an adjacent state might be 100. It would only differ by the A flip-flop, say, being a 1. Or maybe 001 or 010 or something like that. All right. And then finally, explain how one might use one hot state assignment. Okay. So the first thing I want to do is talk about a situation that might come up where you can actually look at all possible non-equivalent assignments. Now, and this applies to a situation with 3 or 4 states. So if you have a problem with 3 states, you'll have, there are 3 ways you can assign the states. And if you have a problem with 4 states, there are 3 ways you can assign the states that allows you to investigate all possible non-equivalent assignments. What do we mean by non-equivalent assignments? Well, what we mean by that is, if you look at 4 states, or 3 states, there are 24 ways you can assign these. For instance, straight binary, 0, 1, 2, 3, or you could go 0, 1, 3, 2, or 0, 3, 1, 2. Those are 3, and it turns out those 3 will give you different hardware. It might, in the end, wind up being no improvement, but they will give you, if there is a difference in the hardware, those will give you all the possible differences. And so out of the 24, there are about, say, 8 of them that will give you one hardware that is somewhat like the straight binary assignment. It may shuffle the gates around a little bit, but you'll still have the same number of gates, same number of inputs. And then this assignment, there's apparently about 8 of the 24 possibilities that will give you roughly this assignment. Again, may shuffle things around a little bit, but this is what you'll get. And finally, the last one, you may get 8 more examples where you would get roughly this assignment. So what I'm going to do, I'm going to work a problem with 4 states, and we're going to go through all these 3 combinations, which explore all possible non-equivalent assignments. And we'll see that it turns out, indeed, some assignments give us less hardware. So let's do that. Okay, so first off, we're going to take a problem. This is a problem where we have a Moore detector that's looking for the targets 0, 1, 0 or the target 1, 1, 0. So these 2 targets. Sorry. And if you look at and the output Z will be 1 only when we get one of these targets. And so here's how this looks. And I'll just think our way through it here real quickly so you kind of understand the problem. So we start in S0 with nothing detected. We get our first value of X. Regardless of whether X is 1 or 0, we're going to go to S1 because since our first item can be 0 or it can be 1, we still have the first item of our possible target sequence. And of course we output Z equals 0, so I didn't put the Z in here, didn't put the Z in here. The only place the Z shows up is down here at the target. All right, so we're in state S1. We're looking for a 1 for our next item here. Note the last two the last two numbers are the same. So we're looking for 1. If we get a 1, we go to S2, and now we have the first two items of our target. But if we get a 0, we go ahead and reset, and we also don't allow overlapping targets. But when we do get our target at S3, we also consider that a reset condition. Okay, so there we are in in state S2, and now we have the first two items. But what if we get, instead of a 1, a 0? In that case, we're going back to S0, and we're back to having nothing. In S2, if we get a 0, we're going to S3, and that's a target. Whether it's 0, 1, 0 or 1, 1, 0, doesn't matter. We still have a target. And I'll put an X prime there. I don't really have to put it there, but it helps to kind of see that, yes, X prime drives us here. If we get an X, we're going to go back around this way. Actually, I guess I labeled that twice, didn't I? If we go back around this way and we get back to S0, where we have nothing. Now in S3, we're going to output Z equals 1, so I write a Z in here. Wherever you see a Z, it means Z is 1. Wherever you don't see Z, it means it's 0. So it's 0 here, here, and here, but here it's 1. No matter what we get, we're going to S1 on the next input, and that's because our next input will give us the first item in the next possible target. All right, so that's the problem. Here's the state table, which, again, you can take directly from the state graph. So S0, on either a 0 or 1, we're going to S1. So S0, on X equals 0, we go to S1. On X equals 1, we go to S1, and we output Z equals 0. Because it's a more. Remember, only one column for the more. Remember, more, our output is associated with our node. All right, in S1, if we get a 1, we're going to S2, but if we get a 0, we're going back to S0. So 0, S0, 1, S2, output of 0. Now in S2, if we get a 0, we're going to S3. And if we get a 1, we're going back to S0 because now we don't have anything using this wraparound path there. And in S3, no matter what happens, we're going to S1, but we do output a 1 because that means we identified the target. All right, that's our state table. Now we're going to substitute in the three possible encodings that give us all three non-equivalent assignments. Okay, and so the first one will be straight binary, 0, 1, 2, 3. The next one will be 0, 1, 3, 2, and the next one will be 0, 3, 1, 2. Notice how the 3 just ramps up. But notice in every case, we still make our initial assignment 0. Now, why do you think we might do that? Well, the reason we might do that is because when we power up our state machine, we want to start in state S0. And so when we make state machines, it's just always a good practice to make the S0 state zeros for your flip-flops. Because if you do that, then you can use the reset input on your flip-flop. You can set up your flip-flops to have a reset, and that reset input then can be asserted for the first, say, 30 milliseconds before then you turn on the clock and you deassert the clear, and you let the state machine proceed from state S0 with the next input and the next clock pulse. And so that's one good way to initialize your state machine. Now, the actual details of that are kind of beyond the scope of the course, so we're not going to really go over that. But that's one reason why we often do make our initial state S0, 0, 0, whatever. In this case, we have two flip-flops, so 0, 0. If we had 3, it'd be 0, 0, 0, and so forth. All right, okay. So here are our three encodings we're gonna work, and this explores all 24 possible encodings, because only 3. You only need to look at these 3 to look at all the different amounts of hardware you might actually get. Okay, and we call these the non-equivalent assignments. Okay, all right. So here's our state table that we got from our state graph, and now we're going to substitute in binary encoding. Okay, so binary encoding. 0 for the first state, 0, 1, 1, 0, and 1, 1. Now, when we substitute this in, 0 becomes 0, 0, 1 becomes 0, 1, 2 becomes 1, 0, and 3 becomes 1, 1. But when we extract this to K-maps, we know that we have to flip these bottom two rows. Okay? when we do straight binary encoding. So let's make that shift if we can. Let's see. Yeah, I think we're set. Okay, and yeah, I do have to gotta get this stuff a little bit. That's better. Okay, and we have to do this. Okay, got it. All right, let me do the transition here. Okay, so hopefully you can see me pretty well there. Yeah, that's not too bad. It is a little bit, maybe like that's better. Even down a little bit, sorry. Okay, how's that? Not too bad. Okay. All right, so the first thing we're going to do, I'm going to try and extract this from the state table. So, and do the K-map. Probably should have just done these on the slides. So the first two are pretty easy, but the third one takes a little bit of work. All right, so this is going to be our DA input. Our DA, and this is going to be our DB. And these, of course, are going to be X and AB, X and AB, and this is to be the DB. And then we have our Z. It's only going to be a two-variable problem, two-variable map, A and B, because it's a more, so X is not directly involved in the output, only indirectly through the flip-flops. And we already know that this is going to put a 1. In most cases, we're going to have a 1 here, and that's going to be AB equals Z, or Z equals AB. All right, so let's extract these. And so this is just going to be, 0, 0, 1, or sorry, 0, 0, 0, 1, and 0, 1, 0, 0, or 0, 0. And then this is going to be 1, 0, 1, 1, and this is going to be 1, 0, 0, 1. So we're going to have a loop here, and then you can loop this one here, or you could do this. It doesn't really matter. And this one here. And so, and then this one here, of course, AB. So let's count them up. So this one we have 2 AND gates, and they're both 3 inputs, 1, 2, 3, because this is going to be, this box is going to be X prime AB. This box is going to be X A prime B. So we have 3 inputs here, and then they're going to go to an OR gate. And so we have 1, 2, 3, 4, 5, 6, 7, 8 inputs, 1, 2, 3 gates. So 3 gates, 8 inputs. This, on the other hand, is going to have 1, 2, 3, 2 variable terms. So 1, 2, 3, 2 variable terms. This one is going to be A prime, B prime. This one is going to be AB. And if we do this loop here, that's going to be X prime A. So we put these in, and they're all going to go into one output OR gate. Again, 1, 2, 3, 4, 5, 6, 7, 8, 9 inputs, and 1, 2, 3, 4 gates. So this is going to be 4, 9. And this is going to be 1 gate and 2 inputs. Okay? That's it. Only 1 gate. So we'll add these up, and that's going to be 3, 7, 8 gates, and 19 inputs. Okay, so now we see that in this example we wound up with 8 gates and 19 inputs. Okay, that's great. Now let's do the next one. So we want to go here. Now we're going to do 0, 1, 3, 2. Now notice in this case it's easy to extract these into K-maps because we flipped these 2 rows already, and so we just put these straight into the map, 0, 0, 1, 0, 0, 1, 0, 0, without even thinking about too much. So let's do that. So I'll do the next one, and we'll do that. So we'll go over here, and I'm just going to extract that into the maps just like we just did. I'm going to have a DA map. And I'm going to have a DB map. And I'm going to have another 2 variable output map. And this is going to be Z. And again, AB here. And this is going to be X and AB. And X and AB. All right. So now we're going to extract it, and it's going to be simple. 0, 0, 1, 0. 0, 0, 1, 0. And then 0, 1, 0, 0. 0, 1, 0, 0. And the B is going to be 1, 0, 1, 1. 1, 0, 1, 1. And 1, 0, 0, 1. 1, 0, 0, 1. Now this is going to be a little simpler. Okay, and then the output map, we're going to see our, let's see, I think, yeah, it's, that'll be 3. So this will still be a 1 there, right? I think so, yeah, I believe that's right. So it's 1 there, so it's still AB. Okay, so this one will just be an AND gate with 2 inputs. This will be the constant B prime, and then we'll have this little 2 group here, which will be X prime A. But then we have these 2 where we have to have 2 3 input AND gates. 1, 2, 3, 1, 2, 3. This is going to be X prime AB, and this is going to be X A prime B. Same as before, actually, I think. And these are going to go down into 1 OR gate for our output. So 1, 2, 3, 4, 5, 6, 7, 8. 3 gates, so 3 and 8. This is going to be a constant B prime and a 2 input AND gate here. And these are going to go into 1 output OR gate. So that's going to be 2 gates and 1, 2, 3, 4 inputs. And then finally this one is going to be 1 gate and 2 inputs. So 3, 4, 5, 6. So it's going to be 6 gates and 14 inputs. 6, 14. Okay, so what you see now is we've solved this 0, 1, 3, 2 setup. Now we're going to shift this this 3 up 1 more, and we're going to do 0, 3, 1, 2. So here we go. Now we do 0, 3, 1, 2. Now this is a little harder to plot. It is a little more of a struggle, but let's do it and see how we do, because we have to do, because in this case, remember, we basically assign substitute all these in, but we really should rearrange the rows in binary order, which means we need to take this row and basically move it down 1. It's kind of what we should do, and that would make the most sense. So if we switch these 2 values, everything will be okay. So we should do 1, 1, 0, 1, like that. So we'll see if we can do that. All right, so I'm going to do the next one. So we'll do the same thing again. Let's see. Yeah. Okay, so here we go. So here again we have the DA map. We have the DB map. And oh yeah, I see what we did wrong. There's something a little bit wrong, but we'll figure it out. And then we have this map. All right, and this is Z, and this is AB. This is X, AB, X, AB, and this is Z. All right, so in this case, the 1 is here. What I should have done in the other map, yeah, maybe the 1's there anyway. Anyway, I think some of these. Yes, in this one it's AB prime. It's A prime. So for this one, it's A B prime equals Z. So actually, the one goes there, actually, because this is 0, 1, 2, 3, and you can see that the down here 2 is the one's lined up with 2, and that's actually also true on this one. So our previous one actually should have been A, B prime, and the 1 should have been up here. And only the first one should have been AB. But anyway, that's fine. I made a little mistake there. But it doesn't change the gate count or the inputs. Okay, so let's do this one. Back to the paper. Okay, so what I have to do is I have to switch those middle two. So it's going to be 1, 1, 0, let's see. So 1, oh man. If I switch these two, then I can just do straight order. That's right. So 1, 1, 0, 1, and 1, 0, 0, 1, because those are zeros. So 1, 0, 0, 1. And then, 1, 0. And then this is going to be 1, 0, 0, 1. So 1, 0, 0, 1. And this is going to be 1, 1, 0. So these have to switch. So 1, 0, 1, 1. All right. And the way this works out, we loop these and get this. We loop these and get this. So we have, in this case, B prime, another B prime. This group of 2 is going to be X, X, A. And this group of 2 is going to be X prime, A prime. So we have an AND gate here with 2 inputs, and we have the variable B prime. Here we have an AND gate with 2 inputs and the variable B prime. And here we just have one AND gate with 2 inputs. This, of course, goes into an OR gate. And this goes into an OR gate. And so when it's all said and done, we have 1, 2, 3, 4 inputs and 2 gates, 2 and 4. Same here, 2, 4, and here 1, 2. Add it up, that is going to be 5, 10. Okay, so now if we go to the next here, we'll see that for our first flip-flop encoding, flip-flop state assignment, we had 8, 19, 8 gates, 19 inputs. For number 2, we had 6, 14, and for number 3, we had 5, 10. So as you see, there actually was a pretty big difference. Notice we went from 8 gates and 19 inputs to 5 gates and 10 inputs in our simplest. So the way we assign our flip-flop encoding for our states does in fact can in fact significantly impact our hardware cost. And of course, if you're designing, say, for programmable logic, that might not be super critical. But if, on the other hand, you're designing for a integrated circuit, that might be a showstopper. Okay, sorry. Okay, so now I want to transition and talk a little bit about why, once we get past 3 states or 4 states, we cannot use this brute force method of looking at 3 possible state assignments to see which would be best. And that brings us to the next chart. So if you'll notice, the number of states, so if we have 3 or 4, they're just 3 distinct assignments. Now remember, there are 24 non-distincts, okay? There's 24 total assignments. But of those, there's only really 3 different batches of hardware to concern ourselves with. In the case of 5 states, there's Lord knows how many actual assignments there are. But let's see, I think it's... So you'll notice if we do, it's basically just 4 factorial for 4 states. But for 5 states, so that's 2 to the 5th, and well, so we have to have. We can get by with 2 flip-flops for 4 states, but with 3 states we have to have 3 flip-flops. So that's basically 2 to the third, and then we have to do that factorial. I think if you take yeah, so you have to take the maximum. You have to take all the assignments, even the don't cares, right? Even though you just have 5 states. So for 5 states, it's not really 5 factorial. That would only be 24 times 5, or what is that? 5 times 20 is 100, plus 20, 120. Okay, so it's more than 120. The number of possible assignments, we really have to take 2 to the cubed, which is 8. So we have to take 8 factorial. And so that's times 6 times 7 times 8. And that gets to be a big number. So it's obviously going to be, yeah, I don't know. It's a big number. Let me calculate it real quick. So you can see over here, it's 40,320 possible states. And of those, there are 140 that are distinct, where you could have different amounts of hardware. Okay, so that's how that goes. When you get to 6 states, it's 420, but the total number of states is getting to be off the charts. And 7, you have 840 distinct assignments. And even when you have this 140, which sounds like maybe you could actually do 140 solutions, but remember, you have to figure out which 140 of the what was it, 8,000 or something, which of the 140 you have to do. That in itself is a little bit of a trick. So that is a bit of a problem. Okay, so sorry. So the problem just grows out of hand very quickly. So what do we do? How can we handle this? Well, what we do is we have rules we follow, and we hope our hope is that the rules will guide us to some savings in hardware. But we can't really do the deterministic brute force solution that we can with 3 or 4 states. All right. So moving on. So we already did that. Sorry. So what we're going to do then is we're going to do some rules, and one of those rules involves this concept of adjacent assignments. Now, what do adjacent assignments mean? Okay, well, we'll look at a super simple example. Let's say we have our 3 or 4 states. All right. So what we would do, we have 2 flip-flops to work with. We have flip-flop A and B. So we make a little table, and we know we're going to make S1 in the 0 state. So S0. We're going to make S0 here, which will be 0, 0. Then this would be 0, 1. This would be 1, 0, and this would be 1, 1. So if we want to say, let's say we wanted, well, let's look at our problem. That's not a bad way to do this, and we'll come back and do these adjacent assignments. But what adjacent means is, if we put, let's say we wanted to make S1 and S0 adjacent, okay? So we would put S1 either here or here, because these 2 blocks only differ by 1 variable, and these 2 boxes only differ by 1 variable. And in a bigger map, let's say we had 4 flip-flops to deal with. Say A, B, and C, D. Then any of these boxes next to each other, we know they only differ by a single variable. Or if you go this way, they only differ by a single variable. So we would work on our adjacent assignments by doing this. And normally, remember, we would normally put S0 here in the 0 state, just because, again, we're going to try and make S0 A equals 0, B equals 0, C equals 0, D equals 0 in this example. Okay? All right. So, armed with that, let's look at our actual problem. Okay, so here we are looking at our original state table, and so let's look at what is our first rule. Let's see. I should go down to it right here. Sorry, states with the same next state. All right, that's our first rule, and the rules are in order of precedence too. This one just affects the output. So states that have states with the same next state. Okay, let's look back at our state table. So do you see any states that have the same next states? Well, yes, I do. S0 and S3. S0 has S1 for x equals 0, and it has S1 for x equals 1. S3 has S1 for x equals 0, and it has S1 for x equals 1. So it behooves us to make S0 and S3 adjacent. All right? So what do we mean by adjacent? Well, so we go over here to our little map, and if S0 is here, we would want to put S3 in either here, or we'd want to put it down here, and that would make it adjacent. All right? What else can we think about? Let's go back to our rules. So we'll go on down. So our next rule states states that are the next states of the same state. Okay, so what do we have there? Here's our state table again. So in S1, S0 and S2 are the next states of S1. So we want to make S0 and S2 adjacent. And here, S3 and S0 are the next states of S2. So we want to make S3 and S0 adjacent if we can. So we'd like to make S0 adjacent to S3 for double reasons. So we definitely want to have that, and we'd like to make it next to S2 if we can. So in this case, the really good thing is that we can do that. So let's look at our little map here. So all we have to do is put S0 and S3, they're adjacent here, and we also wanted to try and make S2 and S0 adjacent. So we just put S2 here. And now we have, here we just go ahead and make this S1, which really didn't show up as any particular requirement for adjacency. So that would be one way to do this. And if you look at it, this actually is 0, 0, 1, 1, 0, 1, 1, 0. That actually is number 3, which had the best outcome. So it just sort of worked out that way. It doesn't always, but you can see the rules do sort of lead us in the right direction here. Obviously, in all honesty, that just came out that way, but there's no guarantee that it would. Okay, we could obviously have switched 2 and 3 here, and it would make equal sense. Okay, so let's go back here. So those are the rules, and then we do have this one rule for the output, and that is states that have the same output should be adjacent. And in this case, the odd man out would be actually usually S, I guess S2, S3 or S2. The one that never has the output associated with it is S1. So that actually works out okay too. All right. So normally, if we only have a modest number of states, like maybe with a 4-variable map, we could do 16 states. If we did 5-variable K-maps, we could do 32. 6-variable, we could theoretically do 64. But once you get past that, you're just going to have to just look at your state assignment and have them only differ by a single variable. Okay. So in our incompletely specified state table, we can definitely use all the don't cares to help reduce our K-maps, and to simplify our expressions. And we can also use them sometimes in state reduction too. Well, we don't usually include the don't cares in our states, but we can include them in our K-maps as don't cares. One more topic to talk about: one hot state assignment. So one hot state assignment is basically assigning one flip-flop to each state. So if you have 10 states, you need 10 flip-flops. If you have 5 states, you need 5 flip-flops. And when you're in state, say S0, flip-flop, say A, is a 1. And when you're in state S1, flip-flop B is a 1. And when you're in state S3, flip-flop C is a 1. But only one flip-flop is ever hot, or 1, at the same time, and all the others are zeros. And so what this does, it does actually allow you to simplify your logic quite a bit. And so sometimes it's a really not a bad way to go, especially if you're doing programmable logic where often you have extra flip-flops not being used. Because most of the time, a lot of our complex logic blocks in say our Xilinx field programmable gate arrays, they have several flip-flops in each block, and oftentimes we don't use them. So you probably will have extra flip-flops sitting around, and you could use them as one hot state assignment. There is one problem with the one hot state assignment, though, and that is it has it. Well, let me see if you can guess it. So remember we talked about how we want state S0 to be represented because it helps us in our reset logic. Right, we want state S0 to be all zeros. Well, if we do the one hot state, S0 is going to have one flip-flop that's hot, which may be throw a little bit of a wrench in our initialization logic. So that is a problem, and that can be one reason why we might want to avoid that. Or sometimes we can just go ahead and do one hot state assignment, but we can have the exception that that our state S0 doesn't have any active flip-flops. So we can do that too. And then we can still use our initialization circuitry. Can just make all the flip-flops go to clear and assert the clears for, say, 50 milliseconds, and then turn the clock and the inputs loose and run the state machine. Okay, I think with that, I'm going to wrap this up. So this is pretty much what we cover in this chapter. And you've now looked at the basic fundamentals of designing a state machine. You've looked at some additional features like how you can reduce the number of states using in a problem that has a fixed number of inputs in hard reset. You can look for redundant states and try and get rid of them. In any problem, you can consider using distinguishing sequences or an implication table, and look for equivalent states and combine them. And if you can do that, you can simplify your problem a little bit, maybe get by with fewer flip-flops. And then we've looked at how flip-flop state assignment can impact the amount of target hardware you have. May be real important if you're trying to reduce the area that your design is going to take up in an integrated circuit. But if you're doing programmable logic, maybe you don't have to spend too much time on that. All right, and you can just do one hot state assignment or binary order or whatever, and it shouldn't really make that much difference. Okay, well, with that, I think we'll end this video.